Hear me? All good? All right, so we can go ahead and start the presentation. This is Daniel and I's presentation on parallelizing the C++ standard template library. A little bit about myself first. My name is Grant Mercer. I'm currently a third-year student at the University of Nevada, Las Vegas. I'm pursuing a bachelor's degree currently. Over the summer of 2014, I did some really cool work with the Stellar Research Group, and that was mainly implementing a standards proposal, which is N4505. And this is a technical specification for extensions for parallelism. And this is going to be one of the two main proposals we're going to talk about during this talk. I worked on implementing this inside of our runtime system, HPX, which I'll get to in a second.
And my name is Danial Bourgeois. I started on the parallel algorithms after Grant had left, so we have just met each other at this conference. But we worked together before to make this PowerPoint for y'all. So I'm currently working for the Stellar Research Group at LSU. And I've worked on the parallel algorithms and in addition N4406, which is parallel algorithms need executors. And so first Grant's going to take it off, and then we're going to talk a little bit about executors, and then I'll hand it back to Grant.
Okay, so first some background information on what the Stellar Research Group is. Stellar is all about shaping a scalable future with a new approach to parallel computation. One of our most notable ongoing projects here is HPX. And HPX is a general purpose C++ runtime system for distributed applications of any scale. So what HPX does is it enables programmers to write fully asynchronous code using hundreds of millions of threads. It's the first open source implementation of the ParallelX execution model. And this execution model serves to overcome the four main barriers of parallelism, which is starvation, latencies, overhead, and waiting. Some focus points we want to get to during this talk are some reasons why we should actually parallelize the STL and why this may be a good idea. Some of the features these algorithms should offer, our experience implementing these algorithms at HPX, some benchmarking results, so we want to make sure that these algorithms actually work as they're intended to, and some future work on what we want to do for these algorithms. So why exactly should we parallelize the standard template library? For one thing, multiple cores are here to stay. The old way of amping up your frequency to gain additional power has long passed. Back in the older days, people thought that you needed to get a higher frequency to have a better computer. And eventually they hit a mark where you start running into memory lag, RC delay, power consumption, and a number of other reasons. So instead of getting more frequency, they decided to make more cores instead. And this was the birth of parallelism. So now we're running into this new era of really great parallel computation, and we need to start taking advantage of parallelism. Another reason why we should parallelize the standard template library is some scalable performance gains. So having a parallel STL gives the user a ton of flexibility because now they don't need to reinvent the wheel when they have these parallel algorithms at their disposal. So if you have large data you would like to run some algorithms on, you can simply say, okay, I'd like to run this in parallel now instead of sequential. So we're still giving you a sequential option, but now we're offering some new options for you. And we want to build widespread existing practice for parallelism in the C++ standard template library. And this is because we're seeing new languages like Rust, Go, and Swift all putting parallelism inside of their core library features. And I think it'd be really cool if C++ could keep up with these other languages and also add some existing practice for parallelism. Here's a small graphic. So everyone knows Moore's law, the number of transistors in an integrated circuit should double every year. And so far it is, but Moore's law will eventually come to an end. There is some work saying that our transistors can only get so small, soon we're going to start hitting the quantum level, and that's when electrons and everything starts getting really weird. So instead, we're starting to see a new Moore's law, and this is for the number of cores inside of a computer. As I mentioned, we're seeing a frequency level out now, so we're not trying to push up our frequency anymore because this gives us more power consumption. So now our power is also leveling out, so this is great for us. Our transistors are still trying to double, which will eventually slow down, but our cores are getting more and more inside of our computers, which is going to give us more power for parallelism. And this is where the standards proposal N4505 comes in. It's a technical specification for C++ extensions for parallelism, which pretty much means it's implementation details for how to get a parallel STL. When you're writing this, it's important to realize that not all these algorithms can be parallelized. We have standard accumulate, for example, where one value will depend on the previous. So this cannot be parallelized theoretically. So it's defined a list of algorithms which should now become parallelized. There's a huge range of them, anywhere from copy to find to sort to transform. So all these algorithms could now be offered to users in a parallel fashion and speed up a ton of new code. It's aimed for acceptance into C++ 17. Our implementation at HPX already takes advantage of C++ 11 and I believe some 14. The components of the specification right now will lie in this standard parallel experimental v1, which is a mouthful. But once standardized, they'll be expected to be placed in standard just as the current STL is. Our implementation in HPX uses the HPX parallel namespace. Now, all these algorithms inside of this new proposed document will conform to their predecessors. So any iterator requirements and return types of the current STL will remain the same. We're not going to impose any new restrictions on these algorithms. This is the simple search algorithms from CPP reference. Nothing will change inside of this new proposal, minus one new argument. And this new argument is an execution policy. So an execution policy indicates the kinds of parallelism allowed and expresses the consequent requirements on the element access functions. So it's pretty much saying you can run this in parallel, you can go ahead and run this in sequential or some other options. We officially support sequential, parallel, and parallel vectorized. Parallel vectorized is to disambiguate the tag, so it'll specifically say this can be vectorized. Here's an example of how this new STL would work. So you have your normal standard vector with v. Let's see if this pointer works a little bit. And you'll have, nope, that doesn't work. So we're going to go back to the presentation. Whoops. Jump right back up there. Okay, so the first two lines are the standard how your sort works currently. And after that is when we're using the namespace HPX parallel. These are our new algorithms we're writing. You have a standard sort, and now you're explicitly saying sort this sequentially by passing in the SEQ tag. After that, and the line after that, you're using parallel execution and parallel vectorized execution. And one of the coolest things about this new proposal is the bottom part, which will allow you to do dynamically selected execution. So if you have some continuously increasing data size, you can set a threshold and you can check, and if the data size is over a certain threshold, you can start parallelizing it. So you don't need to know the type of parallel execution you want to do at compile time. This can be a completely runtime dependent operation. And then down below, I don't know if you guys can see that, or I believe you can. We're simply passing in this blank execution policy, which has been set to either sequential or parallel. Some things to note about this new parallel execution policy inside these algorithms is that it's the caller's responsibility to ensure correctness. So we're not doing any work to make sure this is thread safe. Anything you do with your own code is your responsibility. We'll simply try and parallelize it for you. So if you're throwing in a data race or a deadlock, it's going to be just as you tried to write your own algorithm. We're not going to try and fix anything for you. So here's a quick example of what not to do. If you're trying to push back multiple elements into a vector at the same time, it's going to give you some undefined behavior. A little bit more about these parallel execution policies is that what we're doing is we're permitting to run in parallel. We're not forcing it to run in parallel. So what this means is that, as I mentioned before, we're not going to impose any new requirements on these algorithms. This is in the case of an input iterator. Input iterators cannot be parallelized because one value, you can't go forward or backward inside the input iterator. What this means is that since we're still going to let you use all the iterator requirements, if you pass parallel, we're simply going to force back into the sequential execution. So this is a case where you might call parallel on a data, some iterators, and these might be inputs, so we'll go ahead and force them back to sequential. Now, for the exception reporting behavior, if temporary resources are required but you don't have them, it'll throw a standard bad alloc. That's pretty normal. And now if the invocation of the element access function, so what actually happens inside the parallelization, terminates with an uncaught exception, for par and for sequential, all the uncaught exceptions will be contained in an exception list that you can use after. Now, what we did different at HPX is, since we're doing a lot of asynchronous programming, we found a new policy would be really useful. We haven't proposed this to the proposal yet, but we found this really useful in our own runtime system. And this is the task execution policy. So what this does is it gives users an additional choice of when they want to join back in with the main thread. It'll return a future of the result as opposed to just the result. And this will allow you to continue doing work and then choosing when you actually want to wait for this work to finish. So it's useful in that if you have some big amount of work you need to do, but you'd also like to do some work while that's happening, you can go ahead and send it off, get a future for it, do some of your extra work, and when you need that value, you can go ahead and wait for it then. So this will be Daniel.
So we've defined a way to interact with the algorithms via these execution policies. But if we look at the code example at the bottom that was in Grant's slide, we're choosing dynamically at runtime whether or not we should do something sequentially or in parallel. But there's more that we can give to the user or more that the user might want to provide. And so this is what my section of the talk is going to be about. And it starts with a proposal about executors to extend where work is going to be done. And then we also want to be able to say how much work is going to get sent to each of our processors, and in other words, control the grain size. And in doing so, we hope to develop abstractions that are useful for the parallel algorithm writers, but also useful for other people who want to make use of these facilities. So N4406 came after the proposal about parallel algorithms, and it's parallel algorithms need executors. So the idea is that we want to be able to control where we want to be able to control where work is done on executors, and we would like a way to do that. So they proposed the .on syntax. So the .on syntax attaches an executor to the policy. So we're creating this interface for the user to interact with the parallel algorithms while still maintaining the same extensibility as the original STL algorithms. So we've got 3 examples on how this could be done, and this is all defined in N4406. So we look at the first one. We have for each call, and we create a parallel policy, but this time we attach an executor, and in this case it's just the default parallel executor. So in reality, instead of doing pair.on parallel executor, you could just do pair, because and what you would expect of pair would be that it defaults to parallel executor. Nevertheless, as an example, I put it there. And you would expect the work to be done in parallel. However, we could also attach a sequential executor. So maybe this is an executor that has one thread or only does work in a way that maintains that order of when it was called. Then we are going to have sequential execution, but we can still send it to a parallel execution policy, because the policy only restricts that it can be done in parallel or sequentially, but it doesn't say it has to be done in parallel. So we want to allow that to happen. But we don't want to allow a sequential policy to have a parallel executor. So that does not make sense. And so we're going to need a way for the executors to be able to advertise what sort of work it's done, or what sort of work it implements or executes. So the requirements to be met. We want to be able to accept an executor, advertise the restrictions, and we'd also like, at least for implementing these parallel algorithms or using executors in general, an API that's easy to use. And this is where Executor Traits for N4406 comes in. There's 4 function calls, and in other words, 2 functions, and they are async execute and execute. Async execute takes a function and it calls that function with the past executor, and it returns the future of the result of that function. But there's also the bulk version of async execute, which would just return a future void representing the function for each of a set of inputs, where input supports begin or supports an index range for N4406. And execute is this analogous sequential or synchronous version. So it would just return a void for execute bulk, but for the normal execute, just the return of the function passed to it. So here's an example of what we envision out of this. We have some executor type, we'll call it exec, some shape type inputs, and in this case we'll say that inputs supports a begin and an end, so we can do for auto v and inputs and so on. We're going to have two functions, f1 and f2, and say they return a type. The second one will have one argument, and typed f for traits to be called traits. And so here are the four function calls, just to make it clear. And if we look at the second one, that will call f2 once for each of the inputs, and it'll use the executor. Now, what I personally find neat about this is that if our executor doesn't implement an async execute with this bulk overload, it'll actually synthesize the async execute bulk overload based off of the async execute provided by the executor. So what's neat about that is that it makes it easier to define an executor. All it has to do is implement async execute. And same for execute and the bulk version of execute. They don't need to define those functions because it can just be synthesized by async execute. However, in some cases it makes sense to define a bulk version of async execute because for an executor it might be easier to implement, create all of these function calls at once instead of just doing a simple for loop over the inputs, in which case the executor traits would default to the executor's function. So inside of HPX, not only did we implement the parallel algorithms, but we afterwards and at the same time, we started doing this proposal. And we really like that we can extend our policies with the .on syntax so that the user has more control. It's a convenient uniform launch mechanism. So only have to create a parallel executor or an executor with an async execute call. And we can do the work in bulk quantities. But we didn't quite like one feature, and that feature was not maintaining the results for the bulk async execute. So let's pretend that one of our F2 calls to one of the inputs takes a really long time, but all of the other calls doesn't take very much time. And let's also suppose that if half of our calls are complete, we can continue with something else. So inside of using this version, if we were to attach a continuation to this feature, then we effectively insert a sequential portion of code because we have to wait for that one really long call potentially, and that might cause a sequential point in the code. So inside of HPX, we decided to change it a little bit, and we added a way to get the future results of our call, and we do that with a vector of futures. And obligatory Amdahl's law graph, the idea is we want to give the user all the opportunity that they can to avoid sequential work. And the idea is that if you have even a tiny amount of sequential work inside of your code, then you're going to have a maximum theoretical speed up. And that's what this graph shows. So here's executor traits inside of HPX, just to give some more clarity about the things it does. It exposes the executor type, the execution category of the executor. So is it sequential or is it parallel? Those are the big ones. Also, the future doesn't have to be the standard future, or even in HPX's case, the HPX future. It can be defined by the executor. but by default, it would defer over to one of the defined futures. And we also implemented our async execute and execute. And in addition, there's apply execute. So we just threw that in so that it uses the executor to call an apply function, which just sends off work, and it doesn't require you to know what the return of that is. And so you save any overhead you might have had from having a future. However, we want to know more information about these executors because they can do different types of things. So we might have an executor that has 3 threads on it, and so it has 3 threads, but we don't know that if we're calling them with the parallel algorithms. So we also added an information traits where you attach an executor, and by default it calls the it by default looks for the executors function for get OS threads or get threads, and it'll use that number to decide how to break up the work. Also, there's other traits just to show it's modular, and there's different things you can expose to the user. So there's timed executor traits. So do something on this executor at this time or after this length of time. And here's our parallel executor. I want to talk about the top part, but first I'm going to talk about the bottom part to get there. And this is just the implementation. All it does is implement async execute, and the rest is done by executor traits, and that's at the bottom. The template stuff at the templated return type and all that says just the return type of the future of the function. And then it calls hpx async with a launch, and that launch can be sent over in the constructor. And so by default, it does launch async. And launch async creates another thread for the function to be run on. But because hpx sort of manages the threads under the hood, that we also expose something that the standard launch policies doesn't, and we call that fork. And so fork lets the main thread of execution take the function call f, and then it lets other threads steal what was originally called on the main. And so that's continuation stealing as opposed to parent stealing. And that was made clear to me by N4409, which is a primer on work stealing. It was very useful for me because I was Googling child stealing and not getting any results. That helped. So when you call async, you're going to create another thread of execution. And so in N3872, they have this example. So you call E and then you spawn F. And if you spawn F with an HPX or an async with a async launch policy, then F will be up for grabs by other processors. And then the main thread of execution will go on to call a G. And then when sync is called, we're going to make sure that F is finished, and then we can continue with H. So if there's no other processors available, the order of execution would be E, G, F, H. However, if we were to use fork, we could change that order of execution potentially. So it would go E. The main thread of execution would then execute F when we spawn it with a fork launch policy, but then G would be up for grabs by other processors. And if we didn't have any other processors, the order of execution would have to go E, F, G, H. And I make this point not just because it was a good primer on work stealing, but because at the bottom, and they explain why this is important, if we have no other processors available and we're using async to launch our NF calls, then that async launch policy will call F n times, so on operations of that function call, so we're wasting a lot of memory. And then once sync happens, it has to go through and call F0 up to Fn. So we can avoid that, and we can limit the maximum number of function calls to be the number of processors available if we use the fork. And so with fork, the main thread of execution, if there's no other processor, just calls F0 all the way up to Fn, and then it syncs. And so here are some of the types of executors that we have so far. obviously, like this thread executor does what you think it does. It creates a thread and it sends its work to that thread. We have the parallel sequential executors, of course, that are defaulted. So if you use a seek policy, then it uses a sequential executor by default. And ditto for parallel policy, then it uses the parallel executor by default. There are also thread pool executors, service executors. And I found this interesting because HPX does locality stuff, so it does stuff on other nodes of computers. There is a notion of a distribution policy, which existed before this idea of policies for the parallel algorithms. But now we can have an executor that we create this executor by passing a distribution policy, and the distribution policy defines how work is done on other localities. And now we've just created an executor that does work on other localities, and it was fairly straightforward to do, and we can treat it like any other executor. So taking a step back, through N4406, have defined a way for launching work. Through the information traits, we can have a flexible decision making, but we still haven't defined a general mechanism for grade size control when we break up that work to be done in parallel. And this was done with the execution parameters. So the idea is that it just has a function that defines how much work should be done given the number of processors available as defined by an executor. So it's similar to the OpenMP dynamic, static, and guided, but we've also used an auto chunk size. And what that does is it measures an amount of work, and then based off of that amount of work, it decides what the rest of the work items should be done. So here is how the user interacts with the parallel algorithms, and it's via these sorts of policies. The idea is that it's easy to make your own type of executor or chunk size or executor parameters. So the first one, we have pair with an auto chunk size. That is also equivalent to pair because that's the default chunk size. We can have our own, so we can have pair with my executor and then a pair with my executor on my chunk size. I think I got that backwards. Pair on an executor with a chunk size, my bad. But at the same time, the policies support tasks, so we can also get future results of our parallel algorithms, and we can use the task policy, and it's just the same way. So in doing this, we've sort of taken some concepts and created those concepts. And so this is just to summarize. There's restrictions. So can this work be done in parallel? Can it be sequential? And that's defined by the execution policy as it was originally intended. But to make sure that the different things that can be done are separated, then we have the other concepts. So the executor defines where work is done. And it also says, hey, I do my work in parallel, or I do my work sequentially. And then, of course, there's the grain size of work. And if we want to do everything on one node or on one block of work, or if we want to do on many blocks of work, we can define that with the grain size. And of course, there's no cost of not using any of these and just using the pair and sequential.
All right, so we had Daniel talk about this great interface for these algorithms and how we now have all this flexibility for them, but we need to write these algorithms. So the thing with these parallel algorithms as defined is they will all take a range and they will all need to be partitioned and some action will be applied on this range. The important thing to note is that since you can do this, you can create partitioners to solve this general problem of parallel algorithms. And in HPX, we wrote 3 different partitioners to implement all these algorithms. Our first partitioner is the for each partitioner. And this is the simplest of them all. What it'll simply do is it will take a range. It will chunk up that range into equal partitions as defined by the amount of cores you have in your computer, or if you specify it a certain chunk size. And it will apply some function f on each chunk. So it's used in a lot of our really simple algorithms. So implementing for each, for example, of course. say fill as well. It'll work by, say you have a range of 12 elements, and let's say you have 3 cores. So what the partitioner will do is it'll distribute that range into 3 equal chunks containing 4 elements each. And you've passed in a function f, and this function f will be applied to each separate chunk. And what that does is it allows us to execute on these algorithms in parallel and solve this problem. So inside of for each n, the simple stuff is the templates we're defining at the top, just some extra stuff. And the reason we call it parallel is because for each n also has a sequential version, because we also want to give the user a chance to just sequentially execute for each n. And then in the middle is the important part when we're actually calling the partitioner. We're forwarding any of the arguments we needed to. And then this lambda function is what will be applied to each chunk. So inside this lambda function, we're looping through that chunk of data, and we're applying that function f you passed into for each n on each separate element of the chunk. At the very end, we're returning an algorithm result of it. So in the case that you asked for a task, we'll give you a future back of that result. And if not, we'll simply give you the iterator back. Next up, we have a partitioner. So this is a little more complex than a for each partitioner. It's got one extra step. And what it'll do is that after we've partitioned this range into equal elements, we'll apply some function onto each chunk, and we'll store the result of that function on each chunk inside of a vector. And then that vector will be passed to a second function. So this is when you have two-step algorithms like find or search. We'll give another example of 12 elements, 3 cores. You'll evenly divide your data up first. And what it'll do next is, what's different here is that you have some vector which is set to the result of each function applied on these chunks. And at the very end, you'll have an additional function passed in which will be applied to the vector v. So this is useful in an algorithm like reduce, for example, because what we're doing is, well, reduce is similar to accumulate, but it can be parallelized. You have the first lambda function like we had last time with the for each partitioner. And what this will do is inside each chunk, in parallel, it'll grab that initial value and accumulate the rest of the chunk. So now what we're trying to do is we have each chunk accumulated, and we need to accumulate the chunks together. And that's what this second lambda function does. So this is the function that will be applied to the result of the vector. An interesting thing that we had with reduce actually was that we had a coworker come in when we finished some of these algorithms, and she needed to write a benchmark that computed the vector dot product in parallel. And what was so interesting is that since she heard about us, she said, okay, we can go ahead and use reduce, for example, because if you were to do this sequentially, let's say you have an array of x values and an array of y values, to accumulate a dot product of this, it would be really easy. You could zip those two arrays together. You could set the initial value of the accumulation to a 0, and then inside each, you could loop through it, find the dot product. Oh, that should actually be a multiply on the right-hand side inside that lambda function. You could multiply the two x and y values together of their location, and then add it onto the result. But we found with reduce, there's some requirements inside the function that actually limit us, and we can't do this. So as you see here in the first lambda function, when we're setting the initial value, that initial value t-val is stuck being the type of the iterator that we passed in. So when you have something like this and you have a zip iterator, the type of the iterator will be a tuple when dereferenced. So what this forced us to do when we wanted to write a dot product is we ended up having to make the initial value a tuple, because when you dereference this zip iterator, you're going to get a tuple of the x and y values respectively. And then during the actual lambda function, this also forced us to do tuple multiplication, because now we had the result on the left side, and then we had our x and y values, and it was a horribly hacky solution, and we didn't like how we finished this. This was the actual solution. We didn't use it, but we finished it. And this is what led us to write a proposal on introducing transform reduce. So this algorithm wasn't initially in the proposal, but while we were doing this vector dot product problem, we realized that this proposal, you would need a transform reduce in cases like this. And we proposed it in 4167, and it was implemented later on, and it's now in the proposal. But what transform reduce does is it'll add in an additional function you can pass. And this function will be used as a convert function. So now inside each chunk, you're respectively getting the initial value, but it's going through a convert function first. So in the case that your initial value is going to be of a tuple type, you can pass it through a convert function and get a double out of it. And now this will allow you to accomplish anything you wanted to do, as you did with accumulate. And then in the accumulation function, after we're grabbing the initial value, we also have to pass in that convert as well to convert each subsequent element. And we came up with a much more simplified dot product in this case. So using transform reduce, we were able to zip the two arrays together, set the initial value to a 0 this time, didn't have to use a tuple. Our addition function was simply a standard plus, so just add two doubles together. And our convert function, so it'll grab that tuple of x and y values, and it'll just find the dot product and return that. So it's simply adding up a dot product, which is found through a convert function. And we really like this solution, so this was a good addition into the proposal. And now on to the last one, and the most complex. The last one had 2 steps, and now this one has 3 steps. The scan partitioner will first partition the data and invoke a function on each equal partition as we do with the other ones. Now what's different in the second step is that we'll invoke a second function once the current and leftmost partition are ready. So this will allow us to kind of overlap our second invocation. And then on the third step, we're going to invoke a third function on the resultant vector of step 2. So this is really specific, but it's for cases like copy if or inclusive exclusive scan, and this allowed us to solve these problems. So we'll do another example. So you have your 12 elements again. You'll partition that into equal chunks. Now let's say this is your current chunk. So you've just computed this current chunk. Once your leftmost one is also ready, this will be stored in a vector v sub 0. And now let's say you move down the chain, so now the rightmost one is your current chunk. And that'll be v sub 1 will be equal to the leftmost and the current. And then you can put those vectors together and apply some function onto that. And that will be stored into R, which is then finally applied to the function h. So this is a 3-step process. It's a little more complex, but it allowed us to solve a problem like copy if. Now the interesting thing when we were writing copy if at HPX is we initially thought it was really simple. I wrote it in like the first week and a half of starting, and I left it. And then maybe a month and a half later, I realized how wrong I was when someone was trying to use it. I'd initially only copied everything that matched the predicate, but I didn't realize that when you're doing this in parallel, you need to start squashing the array after. And this became a problem because using the other partitioners, I would have had to do 2 separate parallel calls. I would have had to copy everything over in parallel and then squash everything in parallel. And this was really inefficient because you don't want to construct resources, execute something in parallel, deconstruct the resources, and then do that one more time. So that's why we created the scan partitioner. And it just so happened that this was really useful for stuff like inclusive and exclusive scan as well. So inside the actual revision of copy if, I couldn't fit the whole function on the screen, but this is just the partitioner call. So we're grabbing the scan partitioner, and inside this first iteration, which we applied to each equal chunk, we're simply flagging any of the elements to be copied. In the second iteration, which will be the current and leftmost chunk, which will be applied to, we want to determine the distance to advance the destination iterator for each partition. And then our last, which will be applied to the resultant of the vectors of step 2, we're going to copy those elements into destination in parallel. So this allowed us to tackle problems like copy if, where you don't have a really intuitive solution to begin with. As well, designing some of these parallel algorithms, we realized that we wanted to start simple and work up the grapevine. So with algorithms like for each, it applies a really good base for building upon other algorithms. And some of these future ones were really easy to write, actually. So you have the case of like fill n, for example. We wrote that in technically 1 line. So a lot of these algorithms are really related to each other in the sense that for fill n, all we needed to do was call a parallel for each n and apply a custom lambda function to be applied to each element. And all this would do is copy over the elements. So what that for each n is actually doing with that boost MPL false stuff, it's just, we have some internal mechanisms. So this will call parallel without having to do any checking. So we know we're executing parallel because we're calling the parallel fill n. And then we're grabbing that parallel for each n and executing that as well. As of today, here are all the algorithms we've completed. We're getting close to finishing up. We still have some of the harder ones to do, such as sort, and maybe a couple others, but we are working on those currently. Hopefully near the end of the year or in the soon future, we'll have these all finished up, and we'll be able to do some complete testing on all these to make sure what we're doing makes sense. And then next up, we wanted to measure these. So after we finished about half our algorithms, we wanted to make sure that what we were writing actually made sense. And this is a quick example of one of the benchmarks we did to measure the performance. This was a performance measure for each. We grabbed some parameters from the command line, and we're looping through and applying some for each function on some data set, which you specify. And then we're averaging out the executions of it. So when we were benchmarking, we compared our sequential, parallel, and task execution policies. It's important to mention that task, we could do something special with them. Because how I mentioned that you can begin choosing when you want to join up with the threads with task, we could overlap our executions. So you have with a parallel execution policy, if you want to call one parallel algorithm right after the other, you would execute that parallel algorithm, wait for that thread to finish, join back up, and then execute the next parallel algorithm. But with futures and tasks, what you can instead do is send both off at the same time and choose to wait for them after, once you've sent both off. So now you can do multiple pieces of work, and you don't have to wait for that first one to finish until you wish to. So in order to get the most out of performance, we wanted to see the typical strong scaling graph. What this means is that on the x-axis, you have a grain size, and on the y-axis, you have a time scale. The grain size means the amount of work you're putting on each thread. If you have a really small grain size, that means you're creating a lot of threads and not putting enough work on it. And this is going to give you really bad performance because you'll get too much overhead of parallelism without enough actual work being executed to make up for this parallelism. On the right, if you're putting too much work on one thread, you're not going to have any parallelism. You're going to put all of your work on one thread, and that's going to be sequential. So there's a sweet spot for every algorithm in that you get the perfect amount of work at the perfect size, and you'll get the most speed up. Now this isn't always known, so we tried to just do an auto partition. So we would grab the amount of cores you had, we would split that up evenly with the amount of cores to try and make use of all of the threads. But some executions, if you don't know how much work actually occurs inside your for loops or anything, it can be kind of hard to tweak. So that's one of the things we are hoping to work on in the future. We used a Marvin node on our Hermione cluster. So the important thing to note is that it's got 16 cores. So in a perfect world, we wanted to see 16 times as fast parallel algorithms. And while we didn't get 16 times as fast, we saw some decent results with some smaller data sizes. So inside each for loop iteration, if we had 500 nanoseconds of delay and a vector size of 10,000, we saw about 10 to 10.5 times fast as a sequential algorithm, which is still great. It's not 16, it's not perfect, but it's still some great scaling. And on the left, you have the typical strong scaling graph where too much work, too less work. Now we wanted to see if we could get even closer to 16 times as fast, so we went ahead and amped up the amount of work. And what we did is we doubled the amount of delay per iteration, and we also increased the vector size by 10, or 10 times the vector size. So we had a vector size of almost, or 800,000 and 1,000 nanosecond delay. And here we saw a lot better results. So now that we have more work to do, it makes more sense to parallelize it. And now we're seeing about 14, kind of near 15 times as fast. And this was really good for us because in a perfect world, we'll see 16. And getting almost 15 is a pretty good sign that what we're doing is currently right, and we can move forward with the rest of our algorithms and try and finish this up. Now the cool thing with that task I mentioned is that now that you can overlap your executions, you've almost got pseudo-perfect scaling. While it isn't actually 16 times as fast, what it means is that now that you're overlapping executions, you no longer have to wait for previous executions to finish before you can launch more. Because I believe for this one, we overlapped maybe 3 or 4 executions. So we would launch 3 or 4 at a time until we waited for the first one. And this gave us some really good scaling results. And it made us happy because it actually makes sense to use a task in some scenarios when you have a lot of work and you may want to do some extra work before you actually wait for it. One of my coworkers, Martin Stumpf, also had a really cool implementation. He had an OpenCL backend for HPX, and he actually used one of our 4H algorithms inside of his work. And this was for grouping work items into work packets. And this was the actual algorithm he used. It was a simple for each, and he iterated over a range and did some function, lambda function on each range. And he saw some really good scaling as well. So this was some of his research in that the speed up versus sequential, if you have a good grain size and a good amount of work, then you can see that you're getting really, really good scaling with our algorithms. And this could come in handy in HPX since we're all about large data asynchronous programming. Being able to suddenly take advantage of parallel algorithms without having to reinvent the wheel could be a big side bonus. So we have all these good pros about C++ algorithms, but we also had a little bit of downside, and we have some future work that we want to do. So one thing to note about these algorithms is that there's a fundamental design issue in that resources will not be shared with multiple parallel algorithms. So it's important to note that if you're doing a lot of these algorithm calls, it's going to construct these resources for a parallel algorithm, go ahead and execute on those resources, and then deconstruct those resources. So if you're doing multiple calls of that, it's going to be difficult to see some of the better performance if you're not sharing resources. And this isn't necessarily a problem with how the algorithms are written. It's just a design implementation to take into account that it's not as efficient if you're calling many of these algorithms at the same time. We also haven't finished all the algorithms, so of course we want to make sure that we finish these. And we also want to perform some additional benchmarking on these algorithms. So we know our for each is doing great, and a couple of other ones are doing great, but we want to get into the more difficult ones like sort, and we want to see if our implementations are worthwhile and if we're still getting great speed up according to all the other algorithms. As well, grain size is important. So right now we're simply just splitting up the amount of work into the amount of cores available. But sometimes if you have, say, a lot of work per iteration, it might not be the smartest thing to just auto partition the grain size. So we're doing some experimental work into seeing if we can somewhat guess the grain size better and see if that will improve the performance as well.
And there's a lot of experimentation that we can do with custom policies. So I have the example that we don't have, but if we have a GPU, then do some work on the GPU. Otherwise, do it on a NUMA domain with this chunk size. But also, we can make policies that connect with each other and use introspection tools that is inside of HPX already. So there's performance counters that measure power consumption. We could also measure how long some function call takes inside of the async execute. And based off of that, we can have an executor that minimizes these things in some way when called with the function repeatedly, or at least called within some grain size inside of a parameters repeatedly. But those are just ideas at the moment. We can open the floor to any questions.
Yes. Well, we do have inner product, I believe, but we found that you have cases like transform reduce. Oh, the question was, why would you not use inner product instead of transform reduce, right? Or yeah, well, we felt that transform reduce would be a necessary algorithm in that inner product could possibly solve that solution as well. But it's good design to have some algorithm that could transform as you reduce over some range. And we felt that would be useful to include in the algorithm list because I'm sure there are some other uses that transform reduce could have over the inner product. Any other questions?
Mhm.
So the question was, why would you not put the execution policy at the end instead of the beginning? And I think that was just design implementation that the proposal writer wanted, because he wanted the how it would execute to be the biggest priority in the algorithm. So whether you want to execute it in sequential or parallel, that should be your first thought before you put in the rest of your arguments. Marshall had a comment?
Yeah, I did have a comment. Several of the algorithms in the STL have multiple forms that take different number of parameters. And if you put things at the end, sometimes you wonder if that may do really quick. If you put them at the beginning, you can look and say, is the first parameter an execution context or an execution method? You have a type trait that says this is one of these. In that case, you know you're dealing with one of those as opposed to any of those. If it's at the end, you start asking, okay, I've got two things at the end. Is this a four-iterated version or a three-iterated execution context? And the matching that the compiler has to do gets a lot harder.
Yeah, so the comment was that there's different sizes in the arguments, so you want to disambiguate whether it's sequential or parallel by placing it in the beginning. The difficulties with sort are just the actual designing how the sort algorithm would work. So I never actually got to the point where I would start tackling sort. We apparently have one person at Stellar currently attempting to write the sort algorithm, but it's mostly communicating between these chunks, because you can't simply sort each chunk, because some data might be in reference to the first chunk and maybe the second one. So we're likely going to have to use something similar to the scan partitioner, where you have these overlapping chunks that you can start communicating in between.
Well, I'm communicating with the person who started doing that, and I think how they did it was, or how they're doing it, is breaking it up into separate parts and then combining them back. But I don't actually know. But it does lead into a problem with the executor parameters, because then it's harder to define. It could use recursion in some sense. So in that case, we might be able to have the user control how deep that recursion can get. But at the same time, that's not really the same as chunking into different partitions that the algorithms currently have. And so that becomes a little bit tricky of how effective the executor parameters are, or if we're just going to scrap them for some algorithms.
And the question was, why is sort hard, pretty much. Any other questions? Mm. Yeah, so the question was, why don't we just give a compiler error if we're trying to parallelize input iterators? And that's because we don't want to place any new requirements on these algorithms. So anything you could have done before, simply by adding the par tag, it should permit parallel execution. So the design thing is, we don't want to force the algorithm to parallelize, we're permitting a parallel execution. So in cases like that, you might not know the types of your iterators, but you can say, I want to permit parallel execution in this case. And you know it won't give you a compiler error, because the algorithm requirements are the same as before. So that's why we decided that. So the question was, how would you need to determine that the algorithm is run deterministically? And I can't give you a solid answer for that. You should see me after. All right, well, oh. So the question was, could you see this tying into data analytics such as MapReduce and such? I can't say for sure because I'm not as experienced in this stuff. I'm also new to parallelism. I'm simply just a student worker that really likes this stuff. But I could see it having applications just due to it's really broad in what we're doing, and it can be applied to a lot of things, and especially the runtime system. The runtime system that we're doing this inside is applicable to applications of any scale. So I could see the work being moved over a little bit.
And to speak to that, there is some work at the Stellar Group about in parallelizing data and file systems. So yes.
Thank you guys for coming.